It is on Thursday. So it is a pleasure for me to introduce our today's speaker, Professor Karam Allali from the University of Casablanca in Morocco. And Karam will tell us today about global analysis of a time-delayed two-strain epidemic model with general incidence rates and therapy. Please, Karam, you can start your presentation.
Thank you very much, Professor Vitaly for the invitation. I would like also to thank Dr. Mozokina for organizing and scheduling the talk. Thank you, everybody, for attending the talk. My talk today will be about global analysis of a time-delayed two-strain epidemic model with general incidence rates and therapy. As the title shows, it will be about multi-strain epidemic model with two general incidence rates that generalize some classical, well-known biological incidence rates. And of course, for the model, we will take into account the time delay for each strain to in order to describe the evolution dynamics of the infection. As you know, many epidemic in the now experience many strain, like if we say, for example, H1N1 is a strain from the seasonal flu, and the late COVID-19 is a strain from COVID SARS-CoV-2, and SARS-CoV-2 itself is a strain. It's a mutation from SARS-CoV-1. Here the outline of my talk. I will start by giving two-strain delayed epidemic model with the general incidence rates. After that, I will give my mathematical analysis of the problem. I will talk about positivity, boundedness of the solution, the steady states, global stability, and the third part of my talk will be about numerical simulations, the stability of the disease-free equilibrium. After that, I will show the results, the theoretical result of the stability of the first strain endemic equilibrium. The third part will be the stability of the second strain endemic equilibrium. The last will be the last part of this numerical simulation will be stability of the last endemic equilibrium. The conclusion will be in the fourth part, and the reference. I'll give some references. Here, the model that choose to describe the generalized two-strain epidemic model will be under the following form. Here we have the derivative, the time derivative of susceptibles, the time derivative of the first strain infected individuals, the second strain of the infected individuals, and the last one is the time derivative of the recovered individual. Lambda here is the birth rate of the susceptible individuals. And here you see here rho is in each equation of the system 1, in each equation of the system 1, which means here we have rho is the natural mortality of all population. So natural mortality of all population is symbolized by the parameter rho. And here I continue. If and here the difference between rho and the mu1 is the death rate caused by the first strain infection, and mu2 is the death rate of the second caused by the second strain infection. Sorry, the D1 is the mortality caused by first strain infection. D2 is the mortality caused by the second infection. Mu1 is the infected, the rate of recovery of the first strain, and U2 the recovery rate of the second strain. And what's it's here is interesting in this model is the two general function f and h, and here we have a f and h. F depends of course on the cystibles and depends also on the first strain infected individuals. H, the second general incidence rate, depends on the cystibles and the second strain infected individuals. And here, if you see here, it's minus, and here minus, and here we have it, this amount. This is reduced from the cystibles and added to number of infected individuals, and similarly for the second generalized second infection is reduced from the cystibles and added to the second strain infected individuals. Here, of course, we have the initial condition are assumed greater or equal to 0, or which it says coincides and it agrees with the biological background of our problem. And to not forget, we have here eta 1 and eta 2. It describes the efficiency of the therapy. Here eta 1 is the efficiency of the first therapy, and here eta 2 is the efficiency of the second therapy. And here we have the last one here, exponential minus rho to 1 is the probability of survival of the first strain from t minus 2 to time t. And here exponential minus rho to 2 is the survival probability from t minus 2 to t for the second strain infected individuals. Here I want to show
excuse me. Yeah. Excuse me, Karam. Can I ask a question to the previous slide?
Yes.
Because not all of our listeners are familiar with such models. Could you please explain this time delay in the equations for infected 1 and infected 2? In the right-hand side of this equations.
Yes, what you have to say? Yes. About
in the equation, in the second equation, in the right-hand side, there is time delay.
Yes.
Could you please explain the meaning of this time delay?
Yes, yes. Yes. Thank you very much, Professor Kitari, for this question. This TO1 it stands for the time needed from the we can call it the incubation period. So when a virus enter to the human body, the person, the individual, doesn't becomes immediately infectious. It needs some time. It is incubated, but this person is not infectious. So it needs some time that the symptoms appear, and sometimes that he can be infectious. He's bearing bearing the virus. The virus is the viruses are inside the human body, but the person cannot affect the other individuals. It needs some time. But my last talk, I think it was about the same model with the exposed two classes of exposed individuals, and without delay. So usually in dynamics, infection dynamics, we model the latent stage, or this latency, by two means. The first mean is to model with the exposed classes, if you have a multi-stream, and the second mean is to model with these delays. So 2-1 is the time needed for the first stream that the population become infectious, and the 2 is the time needed for the second stream to be infectious. Here we have two classes of infected individuals, A1 and A2. There is some mini stream for when the disease. There is, for example, the mini strain in the same disease, the same overall disease. There is some mini strains that can emerge, and this kind of models try to understand the coexistence, the condition of coexistence, and the condition of coexistence, like for when the disease have many strains. As I said before, for example, H1N1 is a mutation of seasonal flu. For example, COVID-19 is a mutation from SARS-CoV-2, and SARS-CoV-2 is mutation from SARS-CoV-1. And what differ from between the classes of this kind of this model was different. For example, there is some strain. For example, it can be some strain is more resistant to other strain. One strain can have, for example, the incubation period is less than other strain. Some strain can be more infectious than other strain, and most important, for example, in many kinds of multi-strain model, is when some strain are resistant to some vaccine. This is for example, you can have the same infection, but for some strain the vaccine is efficient, but for another strain the vaccine is not efficient. This kind of model can help to understand this endemic evolution during time. Indeed, it's difficult to predict a large time. This is the problem of mathematical models. It's very difficult to predict very some large time further. For example, if we see in the weather, the modeling the weather, it can predict only some days, for maybe some weeks, but anyway, it can predict some some evolution for short or maybe medium period. Go further to this.
Yes, please. Yes, please continue.
Yes, thank you. This is the flow chart of this model. So is here the arrow go inside the compartment is the increasing. So S will be increased by all arrows coming inside, and the number of staples will be decreased by all arrows going outside. So here the staples will be increased by this birth rate, and will be here the natural mortality row, and here we have this infection. So the two general incidence of infection. So if we have the first force of infection F, so it will go to I1. If we have the second force of the infection H, it will go to the second infected individual class I2, and the dashed arrow, it means the delay. Here we have the delay, so it goes from here we have the delay. So here -2 1 -2 2 1 -2 1 with the probability of survival from 2t - 2 1 to 2t, and the similar thing for the other string. As you see here, row go outside, row both for classes row. It means natural mortality of all the population, and here D1 is the mortality caused by the infection, and D2 is mortality caused by infection for the second class of infected individuals. Here, µ1 is the rate that first strain infected, the rate that the second strain I2 become recovered. And here I wanted to check, for example, in µ1 and µ2 and µ2 population. This is called therapy. The efficiency therapy, for example, we can say here, if µ1 is equal to 1, it's 100% efficient. So all this infection becomes 0. If it's 0, it's the treatment is not as efficient at all. Oh, okay. It's if eta 1 is 0.5, it means it's efficient 50%. Here the incidence rates verify these 3 conditions. If the susceptible is 0, so F and H is equal to 0. F is slightly increasing with respect to the first variable S, and here it's decreasing with respect to the second variable I1 and I2. Of course, we need to give some examples of this the incidence rates. The simple incidence rates, we call it bilinear incidence function. Is alpha multiplied by S multiplied by I. I think it's the first. We find it in the first epidemic model suggested by Kermack and McKendrick in the 1927, and later many incidence rates were suggested. For example, here the saturated infection incidence function. It seems to be more biological than the bilinear incidence function, but because sometimes it grows, the variable can grow in non-controlled manner for the first example. However, in the second saturated rate, we have some saturation, and the saturation it has two ways to describe saturated incidence rates. Alpha at hi divided by 1 plus sigma 1 s, or the second way, alpha si divided by 1 plus sigma 2i. Was the difference between the two incidence saturated incidence function. Here we divide by some expression depending on s, and here we depend on some expression divided by I. Biologically, when we can, what is the importance of like this kind of saturated incidence function? Is look, for example, we have some situation, we have some population crowding population. For example, we can have some population crowded near the susceptible are crowded near one infected individuals, or the infected individuals are crowding near one susceptible individuals. So this saturated acid infection can have this like this form, or some psychological or some psychological effects. Here we have Bedent and De Angelis incidence function. It's take into account the two kinds of the saturated incidence function. If we look here in this form, we take the form of the first saturated incidence rates and the form of the second unsaturated rate. So we can add both of them. We add sigma 1s, and we add also sigma 2i. Here we have it's more general than the saturated incidence rate. And here Claury Martin, it's more, of course, it's more general than the Bedent and De Angelis. So if here we have both of we have here 1 plus sigma 1s, 1 plus sigma 2i, and both of them si, and there is some works that takes this sigma 1 and sigma 2 equal to sigma 3, and there is some name of this saturated acid function. The last one is non-monotonic incidence function. We divide by square of I instead of dividing by I. Here's some literature that's about two stream. Here we have two stream. It's studied by Baba Hensel and Vintalov Amin. With taking one is bilinear. Why beta s? Because here we have in this model, in our model, we have f SIE multiplied by I1 and IH multiplied by I2. So here in this, we have removed this I from each incidence. This is why F as I is equal beta S. But in the model, it take into account beta S multiplied by I. And the two incidents are non-monotonic is studied by Miskaf Khayat and Alali, and we generalize two incidence function without delay. It means that we have exposed, it's studied by Khayat and Alali. And the tree stream, it's also have some it's also studied when we without delay, and we're taking into account exposed the classes. For the biological systems, we need to prove first that the model exists, existence of the posedness of the model. So we should prove some properties. For example, the cell dynamics and individual dynamic, population dynamics. Cells or population are usually always the number are positive, of course, and they are bounded. So we need to prove this boundedness, which ensures the well-posedness of the model. For the initial conditions, phi I belong to C plus. C plus is the continuous set from T minus 2 onto R plus. For example, this is the initial conditions, because the initial conditions are defined in an interval, because we have the problem of time delay. The time interval not defined on one point, it's defined on one interval, an interval. So here the problem one has unique, positive, and bounded solution as I1, I2, R for R t greater or equal to 0. Moreover, we have t, it's less or equal to t0 plus lambda divided by rho, and we have RT less or equal R0 plus nu divided by rho, norm infinity of I1 plus norm infinity I2, with nu is sup nu1 nu2. And here we have T is having this form. Why we take this form? We take this form because if we take the derivative of all this form, the general incidence function will disappear during the proof. So if we multiply I1 by exponential rho 2 to 1 and exponential rho 2, and we add 3 of them, we will have the incidence function will disappear, and we will have this form is derivative of t, the sum of the three first classes, less than lambda minus rho t. So from this, if we integrate this form, we will have the fact that t is bounded. Similarly, we inject this result to the last equation, and we have the boundedness results of R. It's clear that the problem has its local solution, because its problem is ellipses, and this boundedness ensures that every local solution can prolong to each time to t greater or equal to z. Here, in order to facilitate the calculation, and we know that R, the first three here, not 5, it's first 3 equations of system are independent of R, so we can omit the fourth equation. The fourth equation, we can omit the fourth equation. So we can have, as a result, we will have only three first equation, which means that we will study only S, and we also study I1 and I2. And here we can have easily the formula of R by N minus S minus I1 minus I2. Here we want to calculate the basic reproduction number. Basic reproduction number is a spectral radius of the next generation matrix. The next generation matrix is the spectral radius of next generation matrix. So the next generation matrix is calculated by F multiplied by V minus 1, V, the inverse of the matrix V. So if we calculate the spectral radius, we will have the basic reproduction number is as maximum of two quantities. The quantity one, first quantity R01, we can it's called the string one, the first string basic reproduction number, and R02 is called the second string reproduction number. Yes.
Excuse me, Karam. There is a question from the audience. If you can ask a question, Anastasia, please, you can ask.
Yes, thank you. I have a question about the previous slide. Can you show it?
I don't. Can you? I don't hear very well.
Could you please show the previous slide? I have a question about this big N. Is N constant? My question is, as it's written in the formula, it seems like N constant, but you have in the model natural death. So the total population decreases with time. And please, could you explain this expression for recovery?
Yes. If we sum all the derivative, thank you for the question, Dr. Mosokina. If here we sum if we sum all, and we go to the model, first model. Here, if we sum all these quantities, as you see, if we sum all quantities, it's not zero. It's the first model of Kerr-McCondrick. If we sum, we neglect the birth rate. So here we have indeed, as you say, we have the birth rate. So the N is the summation is not constant. What I want to say in the same model here, I want to, if we solve three equations, we can have I1 and I2. And you don't have R in the first equation. If you see the first equation, we don't have R. So if we solve these three equations, we can have I1 and I2, and we inject I1 and I2 in the first equation, and we can have R. And I didn't say that the summation of all compartment is constant. So of course, thank you for your remark. N is not constant. It's all. I want to say, just if we can have this if we know these quantities, we can know R easily. And the three first equations, we don't have R, so we can work in the three equations. And if we know I1 and I2, we can know easily R.
Okay, thank you.
Okay. Thank you for question. I will continue. Here we have two quantities. We have the quantity R01 and R02. R01 is called the first string basic reproduction number, and R02 is the second string basic reproduction number. Why we give these names to these quantities? Because R01 depends on the characteristics of the first string affection, and R02 depends on the second string characteristics, like the mortality rate, the delay rate, total, and the recovery rate of the second. R01 the same. Similarly, it depends the characteristic of the first string infection. It means the mortality of the first string, the death rate, the death rate caused by the first string, the delay, the toll, the time, the delay for the first string to have that the person become infectious, and of course it depends on eta 1 and eta 2 therapy. The therapy. I want just to say that we have worked in this with with the two colleagues without therapy, and it appears in journal Hausa Solitans and Fractal in last year. So what I want to add here, just simple, try to see what happened if with the therapy, especially if numerical simulation. The steady states. So we need to know the steady states. Why we are interested by the steady states? Because usually in biological dynamics, we need to see what happened after if the infection dynamics will go after several times. What happened if a large time if it go to the extension of disease, it goes to the persistence of disease, it goes to persistence but only for some strain, it goes to persistence for the other strain, it goes to persistence for all strains. This is why the steady states is very important to calculate for the beginning. So here the system 2 has unique disease-free equilibrium E0 and 3 endemic equilibria under the following conditions. If R01 is greater than 1, then the strain 1 endemic equilibrium E1 exists. If R02 greater than 1, then the strain 2 endemic equilibrium E2 exists. And if both greater than 1, then both strain endemic equilibrium ET exists. In order to find the steady states, of course, we solve the problem without the time derivative. It calls this is why you call steady states. This is not time derivative, and we can see here when we arrive to, even for the numerical simulation, it will be the curve will be steady, constant. So there is no derivatives. This is why we solve the system without time derivative. And we solve only the three equations. And if I1 and I2 we obtain that this is free equilibrium. This is very easy to find. This is very easy. This is lambda divided by rho. But if one is not first affection is not equal to 0 and the second while the second equal to 0, we will have this formula. This formula, it's easy to find. E11 equal to lambda minus rho S1 star. It means that S1 star will belong to, because I1 is positive, so S1 star will belong this interval. This is a condition because we need that I1 star is positive. This is a condition. So we have this, and we have this, and we have A2 1 star is 0, and similarly for the other the second string endemic equilibrium is defined by the same manner, and the last string is given by this formula. We have ST, the total star, I1 total and I2 total, and we have this this equation. This is free equilibrium A0 is globally asymptotically stable if R0 is less or equal 1. Usually this is what, for example, when the world population experience COVID-19, and each country has calculated this basic reproduction number, and it was in some countries 2 dot, if I remember right, 2 dot something, which means that one infected individuals can infect for example, it can affect two other infected individuals. This is the definition of the basic reproduction number. Is how many one affected individuals, how many it will affect in an entire population formed only by susceptibles. So the epidemiologists need that this basic reproduction number is less than 1. So here, if R0 is less than 1, so either this is free equilibrium, is globally asymptotically stable. The idea of the proof is to take the following Lyapunov function. The following Lyapunov function is equal to all this this form by we can, because here we have the time delay. This is why we take this form of integral to have both. If we make derivative of this form, we can have the forms of the infection given in the first and the third equation in the system. It will facilitate the calculation. This is why we make the integral between 2 minus 2(1) to t and t minus 2 to t. This is very important. When we make a derivative, it will be easy to calculate to find the dependence on R0, and if R0 is less than 1, we will have the derivative of the Lyapunov function is negative. Its Lyapunov function is like it's like energy. It's like energy that's when the energy it's decreasing. So like a ball. So we can make a ball. So if energy is decreasing, the ball will go to the steady states. Otherwise, it will increase indefinitely, and it will be unstable. This is the idea of to take the Lyapunov functions. It's a very powerful tool in order to demonstrate the global stability of the steady states. The strain 1 endemic equilibrium E1 is globally asymptotically stable if R01 is greater than maximum of 1 and R02, and the same similarly to the first proof. We take here the integral, some integral between t minus 2 to t minus 2 to t. And if we make the derivative, here we have phi x is equal to x minus 1 minus ln the x. It's a positive, this function, because function logarithmic function is below this curve x minus 1. And we make derivative of this Lyapunov function, and we'll have this it's negative, so it means that the strain 1 endemic equilibrium E1 is globally asymptotically stable when R01 is greater than maximum of 1 and R02. The strain 1. The strain 1, the same thing. Here we have the both strain endemic equilibrium is globally asymptotically stable if R0 is greater than 1. I want to recall that R0 is the maximum of R01 and R02. It means that both of the two strains are greater than 1. I want just to mention one thing. Here, in the deterministic models, this is make the endemic equilibrium stable. But for some stochastic models, it doesn't mean. It means, but we need not to become slightly increased by 1. In the stochastic models, we need to be more and more increased than 1. So the statistic models, we need to calculate another stochastic reproduction number. So which means that if we are slightly more than 1, even for a numerical simulation, 1.1, 1.2, this is free equilibrium stable. I'm talking about stochastic, but we need to go larger than 1. It comes for them some stochastic cases like some unpredictable situations. And here we have the Lyapunov for to prove that this we need the Lyapunov function LT given by the following formula. As you know, Lyapunov function has some properties. It's 0 in the equilibrium, and the derivative is less. The most important property is this energy is not increasing during the time. It's decreasing. Here for simulation. So for the numerical simulation, I have concentrated to 2 cases. The cases both of the 2 functions are bilinear, and the 2 cases non-monotonic function. Here, the initial condition theta, S theta equal to 3. as well known for the delay problems, mathematical delay problem, we need some condition on an interval, -2, 0. And we have take just constant in this it's like initial condition. And here I have take 2 equal to maximum 2, 1, 2, 2. And we have chosen the following parameters for the numerical simulation. Here, this is the work is concentrated only on the effects of the therapy, because the work without therapy is done with Farah Amin Allali in last year. So here I have chosen to change the value of the therapy. Here, if we take the therapy is 90% efficient for about the infection. If it's 90% efficient, so the curves go. The blue curve go. It's bilinear incidence rates with the numeric simulation with bilinear incidence rates, and the dashed curve is non-monotonic incidence rates. If we see here, the susceptible go to their maximum values, their maximal values here, and we check here. If we want to check here, it's lambda divided by rho. Lambda divided by rho. Go see the maximum value. It's just a manner to check the numerical simulation and with the theoretical part. However, for the first strain infection individuals and the second strain individuals, it goes to 0, as well as the recovered individuals here goes to 0 for both incidence rates, bilinear incidence rates, and also non-monotonic incidence rates. Here we change. We leave. We let 90% of eta1 treatment efficient, and only eta1 is not efficient. So we can have here that extension. We see here extension of the first strain disease, while the second strain is persistence. We have persistence. It doesn't go to 0 for the both incidence rates, bilinear or non-monotonic incidence rates. And here we have the susceptibles, the behavior susceptibles, like what you see in the top left. The recovered stay on the positive level. And here, what is interesting is this curve down left is all the curve go to 0 for the bilinear incidence rates and also for the non-monotonic incidence rates. Here for the second strain, so we can make here 90% for eta1 and 0.001 for eta2. We make the opposite. We choose the opposite here. So we make the opposite, which means that eta1 is equal to 0.001 and eta 2 is 90% efficient, which means that I2 go to 0 while the other variables stay at the positive level. And here the last numerical results concerns the dynamics of the infection, showing the both serine endemic equilibrium stability, which means that eta 1 is equal to 0.001 and eta 2 it's equal to 0.001. So both for all the curves, it's the persistence for the first strain and the second strain. And here we have in the bottom curves, we have the bottom curves. Left I1, it's stay at positive level, it doesn't vanish. And here the I2 and bottom curve, it doesn't vanish also. So it stay in positive level. And here, as a conclusion, we have talked about the well-posedness of the problem. I have talked about that demonstrated in the term of positivity bondedness in the positivity bondedness of the solution. The problem, we have proven that the problem admits 4 steady states, namely the disease-free equilibrium, the first strain endemic equilibrium, the second strain endemic equilibrium, and the both strain endemic equilibrium. The global stability of the problem have been proved depending on the basic reproduction equilibria. More exactly, depending on the first endemic equilibrium and the second endemic, the first basic reproduction number and the second basic reproduction number. We have used it to prove this, some suitable Lyapunov functions. We have carried out some numerical tests in order to show the stability of the equilibrium, and more precisely to see the efficiency of each therapy on the disease. The therapy efficiency plays an essential role in decreasing the number of infection individuals. And the strain therapy may change the nature of the equilibrium stability. For example, if we change one parameter, it's one equilibrium lost its stability, and the other equilibria it became stable. It is the kind, I think it's kind of bifurcation. It's a kind of bifurcation of if you change one parameter and the nature of the stability equilibrium change. So can be taken as a key parameters like the eta 1 and eta 2. Here's some references, and I want to say thank you everyone for attending the talk.
Thank you very much, Karam, for this interesting presentation. We have some time for questions, so please, if there are questions from our audience, you can ask. And I will start our discussion. Anastasia, please.
Thank you very much. I have a question about last slides. Could you please show the for example, the last slide with the plots with stability of endemic equilibrium in the case of, yes, this one. We have some not symmetricity here for I1 and I2. Could you please explain why it's like this? This is my first question, why they are not symmetric. And the second question is, I don't know whether it's question or maybe it's just my wonder or comment that the unstable case, the susceptible are not zero. So why do not all the population goes to the infection? What you have in your equation that not all the population.
Sorry, Dr. Mozokhina, I understand the first question. And the second question, the first question is why they are not symmetric. And the other question is?
The other question, why the susceptible is not zero?
The susceptible.
Yes, when we have endemic equilibrium of both strains, why not all the population become infected?
Why they are susceptible are not zero here?
Yes.
If I understand this, I will the second question. If I understand the second question here, if we see here the theoretically. Theoretically, we have this. For example, we take the susceptible. It belongs to 0 to gamma divided by rho. So theoretically, we are not sure that the susceptibles go to 0.
Can I add to this question, please? Karam, could you show, please? Karam, could you show, please, the
yes.
model, the equations?
Yes,
Yes, for example, yeah. Yes. I think that susceptible are not equal 0 because of this minus rho s term. If we forget, Anastasia, if we forget about this infection epidemic, we have lambda minus rho s. So s is not 0 here. If we add infection, so it decreases the number of susceptible, but because of this negative term, the number of susceptible remains positive. In the other words, because we always have this lambda, we have new susceptible coming.
Yeah, I understand. Okay. So, yes, we have the newborn, so when they become infected with some rates, because we have newborn, we have not 0 susceptible as equilibrium. Yes, I understand. Thank you. And why does the cases I1 and I2 are not symmetric? You choose some parameters that are not equal for these cases. Yes.
I will go to the slide showing the numerical simulation. You have asked me why I1 and I2 are not symmetric.
Yes, changes from each other.
I will tell. I really don't know.
No, but because parameters are different. For example, you have eta 1 and eta 2 are different. No, eta 1 and eta 2 are the same, but maybe some other parameters are different, or maybe incidence functions are different.
Because the structure of form.
It depends to the parameters, yes, of course. But why, especially why they are not symmetric?
But the parameters.
About the parameters.
But the parameters are the same or different for these two, for I1 and I2 parameters here are the same or different?
What I want to say is I was interested in the disease extinction and the persistence, but Indeed, it's a good question. If maybe we need to see with my colleagues to see this kind of symmetry and even the dynamic, and even to try to plot I1 and I2 in the phase plane. Maybe it will give some rich dynamics. I really maybe it will be subject to some future directions. But as Professor Cortes said, is maybe it's parameters. The parameters make this kind of situation. Let's say that.
Okay,
Yes.
I understand. Thank you.
Well, I listening, Karam, to your presentation. There are many interesting things. In particular, I was very much interested by the construction of Lyapunov functions. Could you please show slide 13, slide number 13? This one, or next slides with different Lyapunov function. Yes, so it's really they're quite complex. So how could you derive? How could you find such complex expressions for Lyapunov functions? Was it partially in some previous works, or because to discover such Lyapunov functions, it's not at all obvious?
Yes, it's not obvious to find some Lyapunov function. Now we are working on other to add some vaccination, but I tell you the truth, it took me a lot of time to find the right Lyapunov function. Even now, several months to see. Indeed, we read the previous works, but to improve the Lyapunov function from the new one, it may take several months. Yes, I think it's the hardest.
Yeah, it's a
part.
It's really
work. Yes.
Yeah, and moreover, it is not guaranteed. It is not obvious that the Lyapunov function exists. It may not exist at all. So you should really have a very good intuition, and I think you really have this intuition to understand, well, to think whether it exists or not, and then to find it. But you have found also others. Could you show the next slide? You have this L1, then L2, but also L3 for the third one, yes or not? Do you have because this is the Lyapunov function for the second endemic equilibrium. No. Yeah, no, this for both of them. Okay, for both, yes. So you have constructed four Lyapunov functions.
Yes, 4.
Yeah. This is really, I think, very interesting and very difficult result to find these functions. So my congratulations. It's really not obvious at all to construct them for such a complex model.
Thank you very much.
And I have also another question. What you mentioned about stochastic models, that in stochastic models, the basic reproduction number, if it is slightly larger than 1, then the disease-free equilibrium can be stable. So is it a numerical result, or there are some analytical formulas? Yeah.
Yes, for our work, we have think in numerical simulation. If we exceed the basic reproduction exceed slightly by 1, in the deterministic curve go to persistence, but the stochastic curves go to extinction. And this results is also in the theoretical part. So we call it the stochastically extension of the disease.
Do I understand correctly that in the stochastic case, it is possible to obtain analytically this stochastic basic reproduction number and its value is larger than 1? Is it true? That, I mean, is it possible to obtain analytically basic reproduction number for the stochastic model?
Updates. What do you mean by updates? Updates?
No, not updates. I think there is a connection maybe with the problem is connection. Is it possible to obtain analytical value for basic reproduction number for the stochastic model?
The stochastic basic reproduction number?
Yes.
The stochastic basic reproduction number, yes, it's calculated, yes. We calculate this depending on the parameters, yes.
And it gives the value larger than 1, right?
Yes. The stochastic basic number reproduction number, if it's less than 1, the stochastic problem go to the extension. But even the basics, the stochastic basic reproduction number is less than 1, the R0 is still slightly, maybe slightly greater than 1.
But if you see that this in numerical simulations, maybe this is a question of time. Maybe you should compute longer time, and then because of the stochasticity, the epidemic will start even if the basic reproduction number is close to 1. Isn't it possible?
Yes.
Okay, thank you very much. If there are no other questions from the audience, then thank you, Karam, again for this very interesting
Thank you, Professor
presentation.
Yes, thank you, Professor Vitali Volpert, for this wonderful invitation. Thank you very much. Thank you for your encouragement. And I want also to thank Dr. Mozokhina for organizing and scheduling the talk. And finally, I want to thank all the attendees for attending this talk. Thank you very much. Have a nice day.
Thanks, Karam. Have a nice day. Goodbye.
Bye.
Thank you very much. Goodbye.
Bye.